students, this is Nitya, Assistant Professor, Department of Mathematics from St. Anne's Arts and Science College. Today we are going to see the Unit 3, Operations on Convergent Sequence. We are going to see the various operations on convergent sequence. We know, as per the previous units, we know that what is a convergent sequence, what is a convergence definition, as well as the sequence, what is a convergent sequence also. And in that we are going to see the operations on convergent sequence. And based on convergent sequence we are going to see some theorems also. Let us see the first theorem. If Sn is sequence and Tn is another sequence of real numbers, then the limit n tends to infinity Sn equal to L and limit n tends to infinity Tn equal to M. Then limit of Sn plus Tn equal to L plus M. That is, if you are taking two sequences Sn and Tn, and Sn has a limit as L and Tn has a limit as M, then if you are adding the two limits, that is, if you are adding the two sequences, then also the limit has to be, the answer has to be L plus M, or the limit of the sum of the two convergent sequences is sum of their limits, or they can be asked in this statement, the limit of the sum of the convergent sequences is sum of their limits. Now we can see the proof of the theorem. To prove that limit n tends to infinity Sn plus Tn equal to L plus M. This is only we are going to prove. For epsilon, given epsilon, that is as per the convergent sequence definition and limit of the sequence definition, for given epsilon greater than 0, we must find n belongs to I such that modulus of Sn plus Tn minus L plus M less than epsilon. We know that the limit of the sequences, generally we will take Sn, modulus of Sn minus L is less than epsilon. Likewise here we are taking Sn plus Tn minus L plus M is less than epsilon, and where n is greater than or equal to n. Take this as a first equation. Now we are going to see the left hand side. Take the left hand side here and take this as a second equation. Here we know that in the question itself they have given that since the limit, that is Sn, the sequence Sn has a limit as L, therefore epsilon greater than 0 there exists n1 belongs to a such that Sn minus L is less than epsilon by 2. This is the limit of the sequence definition. Likewise we are taking for Tn also we are taking as a n2 as a real numbers. Rest of all positive integers we are taking. So epsilon by 2. Now we are taking the maximum of n1 and n2 because we are going to see the convergent sequence. So we are taking the maximum of n1 and n2. Therefore the 2 implies modulus of Sn plus Tn minus L plus M, which is equal to Sn minus L plus Tn minus M. So this is less than or equal to modulus of Sn minus L plus modulus of Tn minus M. Therefore this is epsilon by 2. Another, this one is we have taken as less than epsilon by 2. Therefore which is equal to, after solving this we are getting epsilon, so which is less than epsilon, and n is greater than or equal to n. Therefore this term, the second equation, can be written as less than epsilon. Therefore limit Sn plus Tn is equal to L plus M. It has a limit, the sequence has a limit L plus M, so hence proved. Next theorem. If the sequence Sn is a sequence of real number and C belongs to R, and if Sn equal to L limit, then limit C into Sn equal to C into L. So if you are multiplying with that sequence C, and also it has a limit the L with C also. So the linear property of convergent sequence. In the examination they may be asking the question as state and prove the linear property of convergent sequence. So you should write like this, write the statement and then go on to the proof. Now we are taking if C equal to 0. So the theorem is obvious. So obviously it will become as a, because the limit has to 0, so obviously it will become as a, the theorem will be proved. That is, it has a limit L. Suppose C is not equal to 0, therefore given epsilon greater than 0, we must find that n belongs to A such that what will happen? See, modulus of Csn is less than Cl, which is less than epsilon. So take that as a first equation. Now we know that since Sn equal to L as per the given definition, so modulus of Sn minus L is less than epsilon by modulus of C. So this modulus of C can be written here the left hand side. So that is, we are taking multiplying modulus of C on both sides. After cancelling we are getting that modulus of Csn minus modulus of Cl less than epsilon. Now equation 1 holds from that limit is n tends to infinity c Sn equal to Cl. So we have arrived at the proof of the theorem. Next theorem, if Sn and Tn are the two sequences of real numbers and if Sn equal to L and Tn equal to M, then limit Sn minus Tn equal to L minus M. For the first theorem, that is 28th theorem, we had seen that Sn plus Tn equal to L plus M. Here only the operations is different, that is a minus. So given that the limit Sn equal to L. So if c equal to minus 1, we are taking the limit c equal to 1, then from the theorem 29, so c into Sn equal to Cl, this is a linear property. So here limit n tends to infinity Tn equal to M. So limit n tends to infinity minus Tn. Since we are taking minus 1, so as per the linear property, so we are multiplying that minus. So minus Tn equal to minus n. Now by the theorem of the 28, the first theorem, limit n Sn minus Tn equal to limit Sn plus minus Tn. So we are splitting that limit Sn plus limit Tn. So limit Tn value, that is minus m, we have taken. So limit Sn minus Tn equal to L minus m. So hence the theorem has proved. So today we have seen the three theorems. One is the operation of plus theorem, another one is the operation of minus, and the last one is the linear property theorem also we had seen. That's the 29th theorem. So go through it, girls.